Hello, my name is Dr. J, and this is my guide to set comparisons. If you would like to follow along by taking notes on slides, go ahead and click in the description. There's a link to the slides. Last time, we talked about set comparisons, in particular subsets and supersets, and we related those set comparisons to inequalities, less than or equal to, greater than equal to, that we use with real numbers. Today, when we talk about set operations, we're going to relate these set operations to our mathematical operations that we know of real numbers. In particular, addition, subtraction, division, multiplication. So, today, while we introduce these four concepts here, we're going to talk about unions, intersections, complements, and set differences. So here's the definition of a union. So the union of two sets, A and B, contains all the elements that are in either of those two sets. We write this union, A union B, with a U symbol, just like that. Mathematically, we could write the union between the sets A and B as the set of all omegas that are either in A or in B. Here's a couple of examples. So we just have two sets, the set that includes the number 1 and the set that includes the number 2. If we take the union of those two sets, we have the set that includes the elements 1 and 2. Another example, the first set has elements 1 and 2. The second set has elements 2 and 3. If we take their union, we get the set that has the elements 1, 2, and 3. You'll notice here that 2 was included in both our original sets, but it is not duplicated in the resulting set. Right? We just get one copy of it in the resulting union. Here is another union. Now we are working with intervals as a type of set. So the first interval is the open interval 0, 1. The second interval is the half open interval 1 and 2, including the endpoint 1. If we take their union, then we get all of the numbers, real numbers between 0 and 2, but not including 0 or 2, which means we have the open interval 0, 2. Alright, so that was unions. Now moving on to intersections. So we have two sets again. The intersection of two sets A and B is the set that contains all the elements that are in both sets. We write the intersection with now an upside down U. I can't really do that with my arms, but I guess it's here, right? Upside down U. Mathematically, we could write that as the set of omegas that are in A and in B. So for some examples here, we have the same example we started with last time, where we have the two sets. One includes number 1 and the second includes the number 2. If we take their intersection, then we get the empty set, because there are no elements that are in both of those original sets. If we use our second example from last time, we have the set 1, 2. We have the set 2, 3. If we take their intersection, then we get the set that just includes the number 2. Just the number that was in common between those two sets. Here is an example using intervals. So we have the open interval 0, 2 and the half open interval 1, 3 that includes the endpoint 1. If we take their intersection, then we get the half open interval 1 to 2 that includes the endpoint 1. Because those are the elements that are included in both of those original first two sets. Alright, the next thing we're going to talk about is set differences. So the set difference between a set A and a set B. We're going to talk a little bit about properties of these set operations, and one of the properties we're going to talk about is whether order matters or not. That is the commutative property. This one, for set difference, order does matter. So in this case, we're taking A set minus B. Alright, so the definition of the set difference then is all the elements that are in A, but that are not in B. We write this set difference with a, I guess that's a backward slash. So A backward slash B. I don't know if I can do that on screen. This way? That way? Must be this way. All right. Okay, mathematically, we could write this. We could write the set difference, A minus B, is the set that has all the elements in A, but that are not elements of B. All right, given our examples, so here's one example. We start with the set 1, 2. We take the set difference, subtracting off the set that just includes the number 2. And we just get a resulting set that has the number 1. Another example here, we have the set 1, 2 minus the set 1, 2, 3. So here's where it's key, is that we just look at the first set, 1, 2, and we get rid of any elements that are in the second set. So the first set doesn't have element 1 in the second set. It does, so get rid of that element. Does it have element 2 in the second set? It does, so get rid of it. Now we're left with no elements, so we just have the empty set. So I mentioned that because you'll notice here that the second set had the number 3. And when we're taking a set difference, that is extra elements in the second set are just irrelevant. Here we have an example where we have the open interval 0, 10, and we're subtracting out the closed interval 1, 2. The most succinct way to write the resulting the resulting set difference of these two sets is to write it as a union. So we have to take that interval 0, 10, and we have to stop at the number 1, right? And so we have the interval 0, 1. Then we have the union of that set with the set that starts at 2, but does not include 2 and runs up to 10. So we have the resulting set difference here is the union of two sets, the open interval 0, 1 and the open interval 2, 10. We know right away that A is a subset of S. Alright, so the complement is all the elements that are in that universal set, but that are not in the set you're taking the complement of, in this case A. We write that as A, which looks like raised to the C power, a complement. And typically, in most problems, this universal set S will just be implied. Mathematically, we can write that A complement is the set of elements that are in that universal set S, but that are not in the set A, which is exactly what our definition of a set difference was, right? Where we have the universal set S with minus the set A. Here's a couple of examples. So we have the set 1, 2, and we're taking its complement. And now I'm listing here the universal set. So for this example, it's the integers 1, 2, 3, 4, 5, 6. So you can imagine this being the result of, say, a six-sided die rolling experiment. All right, so you want the complement of the set 1, 2 in this universal set of integers 1 to 6. Right, well, the elements that are not in that set A, but that are in S are 3, 4, 5, and 6. All right, let's take a similar looking result, or similar looking example. We have the set 1, 2, we're taking its complement just like we did before, but now the universal set is the natural numbers. Now I want to remind you as you're thinking about this problem that we are defining the natural numbers to include 0. So we have the integers 0, 1, 2, 3, and so forth. All right, so the complement is all the natural numbers, but not 1 and 2. And so we have 0, then 3, 4, 5, 6, and so forth. Here's an example using an interval. So here we have the interval 0, 10, the open interval 0, 10, and we're taking its complement in this case, r plus, which we had defined previously as the open interval 0 up to infinity. That is all the positive real numbers. So the numbers that are not in the open interval 0, 10, but that are in r plus are the numbers 10 up to infinity, including 10. And we can write that as this half open interval, 10 up to infinity, including the endpoint 10. All right, so as we think about these properties, you should be thinking in your head properties that you're familiar with these standard mathematical operations of addition, subtraction, multiplication, division. Things like if you add 0, you get a number back. If you multiply by 1, you get the same number back. If you are adding or multiplying, then order doesn't matter, whereas it does matter if you're doing subtraction, division. These kinds of properties, and we're going to relate these kinds of properties to sets right now. We start with the identity property. So if we take a set A and we take its union with the empty set, we get back A. If we take a set A and we take its intersection with the universal set S, then we get back A. So that's the identity properties here for unions and intersections. We have a commutative property in terms of order mattering or not. So unions, order doesn't matter. You can take A union B and B union A. It doesn't matter for intersections, same thing. But it does matter for set differences, right? And therefore for complements as well. We have the associative property. So the associative property here deals with when you do repeated operations of the same kind. So in this case, all unions, just like if we were doing all additions. And here, if you're doing all unions, you can decide what order you want to take those unions in. So in this case, we have A union B, and then we take the union with C. On the right side of the equation, we do B union C first, and then we take the union of that union with A. And a similar result holds for intersections. The next property is the distributive property. Now, this is a situation where you have two different operations. So you have unions and intersections in the same side of the equation. So in this line here, we have A union, B intersection C. Well, we did that B intersection C first. And now, in order to distribute, what we're going to be doing is we're going to be distributing that A union to both the B and C sets. So the result is that we have A union B and A union C. We're going to take the intersection of those two unions. We have a similar result for intersections and unions where we just swapped those symbols in the equations. All right, the last property is one that's not so analogous to standard mathematical operations and their properties. Here we have A, and we take its union with A complement, and we'll get back the universal set S. If we take A intersection A complement, then we get the empty set. That's because A cannot have any elements that A's complement has. All right, so here's a number of properties, and we have one more set of properties that kind of relates unions, intersections, and complements, called De Morgan's laws. So on this page, we have two sets A and B, and they are both subsets of S, that is the universal set, just like we had on the previous slide. So here we have one where we're taking the A union B, and we're taking the complement of that union. And De Morgan's law says that that's equal to A complement intersection B complement. And now we have another version of De Morgan's laws that just switches the union and intersection. So A intersection B complement is equal to A complement union B complement. And now I want to give you an example of why you might want to use this relationship. So here's an example where we're supposing the universal set is the open interval 0, 10. We have a set A that's the open interval 0, 2. And we have a set B that's the half open interval 1, 3, including the endpoint 1. And what we're interested in doing is perhaps calculating A complement union B complement, right? That is the right side of that first equation. So let's try to do it. All right, so what's A complement? Well, that's not too bad, right? The universal set is 0, 10, A is 0, 2, so the complement will have 2 up to 10, and it will include 2, right? So there we go. So we have A complement. Now let's get B complement. Okay, well, this is a little trickier. So we have the universal set 0, 10. We have B is the half open interval 1, 3 that includes 1. So certainly I want to include the numbers 0 up to 1, but not including 1. And then I want to include the numbers 3 up to 10, but including 3. And so I guess I'm going to have to write that as the union, right? So we have 0, 1, union, 3, 10, where the second interval includes the endpoint 3. All right, still not too bad. Okay, now we have to go to the next step. We now need to take the intersection of these two complements. Okay, so we have A complement intersection B complement. Well, let's just write in what A and B are. All right, there we go. So now we have 2, 10 intersection, parentheses, union of 0, 1, and 3, 10. But I know the distributive property, right? So I can distribute that 2, 10 intersection through. All right, so let's do that. So here we have 2, 10 intersection 0, 1, and we have 2, 10 intersection 3, 10, and we'll take the union of those two intersections. Okay, so let's see. The first part, we have 2, 10 intersection 0, 1. Well, there are no elements that are in both of those sets, so the intersection there is going to be empty. The second intersection, we have 2, 10 intersection 3, 10. The only elements that are common to both those sets are the interval 3, 10, including the endpoint 3. All right, not too bad. We have the empty set and we have the half open interval 3, 10. And the last step here is to take their union. But if we take the union of something with the empty set, we just get back the original. So we have the half open interval 3, 10 that includes the endpoint 3. Whew, that was a lot of work. Okay, so De Morgan's laws can come to the rescue here. We can make this a lot easier by using De Morgan's law. So if we're trying to calculate the right side of this first equation, let's just do the left side because De Morgan's law tells us that they're equal. So the first thing, A union B. Okay, so A union B, A is 0 to 2, B is 1 to 3, so the result is going to be 0 to 3. Great. We take the complement in S. All right, so we have 0, 3. We want everything in 0, 10, not including 0, 3, so we have 3 to 10, and it includes 3. Right there. All right, so you can see here that the first approach, where we calculated the right side of that first equation, was much more laborious. right? But the second approach there was actually relatively easy. And so here's an example using De Morgan's laws would have saved us a lot of time. All right, wrapping up for today. We introduced today some set operations. We introduced union, intersection, set difference, complement. We introduced a number of properties, the identity, commutative, associative, distributive, complement, as well as De Morgan's laws. All right, so hopefully you've gotten a little better understanding about set operations. Definitely the best thing to do is to do some exercises to practice. If you're still very confused, next time we will be talking about Venn diagrams. Venn diagrams are a graphical illustration of these sets, and we can graphically illustrate the ideas of the set comparisons, that is subsets and supersets, and these set operations using those Venn diagrams. So if this is very confusing to you, go ahead and take a look at the Venn diagram video that I'll put up next. As always, have a great one.